Hi, and welcome back to Earth Materials. Today I want to talk about ores and ore mineralogy. And I'm really not going to talk about all the different types of ores that could be formed on Earth. I really just want to talk about two main types. One is massive sulfides, how they form on the seafloor, and their comparison to volcanogenic massive sulfide deposits, which are on land. And then I want to talk about porphyry copper deposits. Those are really important in the western United States. The last thing I want to talk about are basic principles of reflected light microscopy. Seafloor massive sulfide deposits reflect seafloor hydrothermal systems. These are really spectacularly illustrated by hydrothermal vents, especially these black smokers here and these white smokers over here. The black smokers have high temperatures, up to 400 degrees C, and these fluids are extremely iron and sulfur rich. These have very high velocity venting. And what happens is the vent fluids mix with water either in the chimney or in the water column to precipitate iron and sulfur rich minerals. White smokers are lower temperatures. The fluid has a different chemistry. It's very barium, calcium, and silicon rich, and it usually reflects slower velocity. In this case, the vent fluids mix with water below the surface to precipitate iron and sulfur rich minerals that depletes the vent fluid in those elements and leaves behind these other elements. An important component of these seafloor hydrothermal systems is that they support chemosynthetic life. So what we see are these large organisms, tube worms here. These can reach 3 meters or 10 feet in length. These clams, mussels, crabs, shrimp, lobsters. All of this is supported by chemosynthetic bacteria, and they live in these other organisms. So the mussels up here in their gills contain these bacteria. That's what these colors are here. They reflect the bacteria in the gills of the mussels. Okay, quick check. What kind of unusual organisms live at deep sea vents? Are they phototrophs, chemotrophs, lithotrophs, or radiotrophs? Would you think, based on what I was just talking about? And the answer is that they're chemotrophs. Strictly speaking, they're referred to as chemoautotrophic bacteria. The chemo part means they use chemical conversions to obtain energy for life. Mainly, this is the sulfur cycle, rather than light. So, as you know, there are photosynthetic organisms, and these are phototrophs. Autotrophic means that they act on carbon dioxide to make organic carbon compounds. Rather than working on other carbon compounds, those would be referred to as organotrophs. So chemoautotrophic bacteria are the basis for life at these deep sea vents. Let's look a little bit more at the hydrothermal system. The circulation occurs because there's a big heat source here, and there's permeable or fractured rock above it. So what happens is water circulates through these systems. It's driven upward by buoyancy in the middle, and it draws in water from the margins through the fractured rock. And these hydrothermal systems are massive. It's estimated that the entire ocean will circulate through hydrothermal systems in only about 10 million years. In general, we divide these hydrothermal systems into 3 main sections. Let me go backwards from here. There's an upflow zone. So this is where buoyant fluids are rising upward and then they're venting out at the seafloor. Something has to replace this water, so that gets drawn in from the side. This forms the recharge zone. So water is recharging in this region and venting in the central region. And in between is a reaction zone. As the temperature increases, seawater reacts with the rocks and creates different mineralogies and dissolves different components into this fluid that is expelled to the surface. So what's the process? Cold water penetrates the basalt. The increased acidity near the heat source in the reaction zone leaches metals and concentrates them in the fluid. Buoyancy causes these to rise over the center of the heat source. And then the venting of the fluid at high temperature interacts with seawater directly to make a black smoker, or it interacts with water that's in the subsurface down in here, and the residual fluid is expelled as a white smoker. So which of the following would be the correct flow path at a black smoker? And the answer here is it infiltrates on the margin, heats at depth, and discharges at a central vent. Discharge on the edges would lead to white smokers. So let's look at the anatomy of a black smoker. Here is a cross-section. This comes from Woods Hole Oceanographic Institute. The plume is buoyant, so it's hot and it's not very dense. And in the first stage at which these fluids interact with seawater, they precipitate anhydrite. Anhydrite is calcium sulfate, CaSO4. The chemistry is very similar to gypsum, but gypsum has structural water. Anhydrite has no structural water in it. The second stage of precipitation is chalcopyrite. Chalcopyrite is a very high temperature mineral, roughly 350 degrees C. And this chalcopyrite is porous, so that means that fluids can penetrate through the chalcopyrite and either precipitate other minerals in the interstices, in the open spaces of the chalcopyrite, or it can actually make it to the seawater and react with seawater there. And then what we see in stage 3 is the precipitation of sphalerite, chalcopyrite, and pyrite. So zinc sulfide, copper iron sulfide, and iron sulfide. And simultaneously, there's a plume that forms. This plume is dominated by fine sulfides and manganese iron oxides, which are black, and so that's why they're black smokers. Here's a cross-section through a black smoker chimney. In the first stage of precipitation, anhydrite and pyrite are forming, so this is the first reaction of the fluid with seawater. Then chalcopyrite forms, and then finally sphalerite forms. We didn't talk about this, but this is a lower temperature precipitation during the waning stages of hydrothermal venting. And there are various other things that happen. The iron sulfides will oxidize on the surface to make iron oxyhydroxides. White smokers are a little bit similar to black smokers in the sense that there's a hydrothermal system. The fluids enter, they react with the rocks, they create this metal-enriched fluid. But there's an initial precipitation of anhydrite, pyrite, and chalcopyrite below the surface. So that precipitation is not occurring at the venting location, it's occurring in the subsurface. That allows the fluid to evolve to a different chemistry. It's more acidic, so it dissolves zinc, gold, silver, and cadmium. Consequently, when it mixes with seawater, it precipitates out a different set of minerals. It's very zinc rich and consequently produces important zinc deposits. So this is the anatomy of a seafloor massive sulfide deposit, SMS deposit. There is a central region that has a lot of pyrite and chalcopyrite. There are chimneys that have that anatomy that we saw for black smokers. There are chimneys that have the anatomy that we saw for white smokers. And there's a cone or apron of fine-grained material that has precipitated from seawater, from these plumes, that rains out and creates this dome structure. So here's an example of one particular vent site. This is at the Mid-Atlantic Ridge. This particular mound, called the Tag Mound, is the size of a baseball stadium, but it has very high concentrations of copper. This would be economically viable. There are two areas that have been studied. Black smokers have moderate concentrations of zinc and moderate concentrations of gold, but white smokers have very high concentrations of zinc and very high concentrations of gold. And this mound has been compared to other massive sulfide deposits, for example, ones in Cyprus, Oman, and Newfoundland. Okay, quick check. Which metals are enriched in white smokers? The answer here is zinc, gold, and barium. Remember that iron and copper are precipitated in the subsurface before the white smokers are expelled. And nickel and cobalt are not the most important elements that are enriched in these systems. So those are seafloor massive sulfide deposits. On land, we have what are called volcanogenic massive sulfide deposits. This is a cross-section through a particular volcanogenic massive sulfide. This one happens to be in Albania, but you can see the same basic structure that we saw for the seafloor massive sulfide deposits. There's a region at depth where there's a bunch of pyrite, pyrrhotite, which is another iron sulfide, and chalcopyrite precipitating, and there are these beds of sulfides which are interpreted to be the rainout from the black smokers. And here's a cross-section through the stockwork, this deeper portion of one of these massive sulfide deposits, showing pyrite, chalcopyrite, and pyrrhotite. Now, most massive sulfides are mined on land, but there are plans to extract massive sulfides directly from the seafloor. There was a company several years ago called Nautilus Minerals that developed all of these exploration prospects in the Bismarck Sea. So this is in the Western Pacific. And they went out of business a few years ago. They were bought up by deep sea mining. But these exploration licenses still exist, and it is still being considered as a potential economic source of copper and zinc. So here is a cross-section that was developed for one of these mining prospects. This is based on drill cores. And here we see a thin layer of deep sea sediments, then a lot of massive sulfides with pyrite and chalcopyrite. And then there is an alteration zone above these volcanics. So the notion is that the hydrothermal systems moved in this direction and precipitated all of these massive sulfides here. The way these are proposed to be extracted is to have these giant abrasive graters that approach these submarine hills and just grind them up. They are then vacuumed up and transported back up to the surface. Now, I was talking about seafloor massive sulfide deposits associated with hydrothermal systems. Certainly, the vents along ridges create these major sulfide deposits. That's what these orange circles are. But there are other types of deposits. There can be authigenic fluids that vent to the surface, and they create these nodules. There can be polymetallic nodules, which are mostly manganese as well as nickel and cobalt. And then there can be these cobalt crusts that are developed along continental margins and also out in these abyssal plains. So I've talked a bit about seafloor massive sulfide deposits and hope that students can now compare them to on-land volcanogenic massive sulfide deposits. Before I go on to porphyry copper deposits, I did want to talk briefly about the types of minerals that host economically important precious metals. So here I'm talking about platinum group elements, silver, and gold. And I know there are silver and gold and platinum minerals that can occur macroscopically, but in fact, most of these metals are mined from other minerals. So for example, tetrahedrite, which is a copper antimony sulfide, there can be several elements that substitute for copper, and in fact, silver-rich tetrahedrite is the primary silver-bearing mineral in northern Idaho. In galena, the same kind of thing can happen. Silver can substitute for lead, although silver minerals can also occur as tiny inclusions in the galena. In pyrrhotite and pentlandite is an iron-nickel sulfide, platinum group elements can substitute into their crystal structures. They can also occur as platinum group minerals as tiny inclusions. And then in pyrite, gold can occur as microscopic growths of native metals or as other gold minerals mixed in with the pyrite or on the surface of pyrite crystals. So although we think of these minerals as economic with respect to copper, antimony, lead, iron, and nickel, they can also be important for silver and gold. To begin the discussion of porphyry copper deposits, I wanted to mention the work of Lindgren. Lindgren was an economic geologist who worked at the turn of the 20th century, and he classified hydrothermal deposits into three types: hypothermal, mesothermal, and epithermal, depending on what he interpreted to be the depth of deposit. Hypothermal deposits form in hot and deep environments, mesothermal deposits form at intermediate temperatures and depths, and epithermal deposits form at shallow depths and relatively low temperatures. The term epithermal is used frequently to describe shallow processes, although they're not necessarily cool. You can have very high temperatures at shallow levels, as we saw, for example, with the black smokers. This is the anatomy of a porphyry copper deposit. So the way these form is they start with an igneous pluton that has disseminated sulfides, typically pyrite and chalcopyrite. So these are just scattered throughout the pluton. When the pluton is exposed at the surface, there is an oxygen gradient between the subsurface and the surface. So very high oxygen up here in the atmosphere, very low oxygen here in the subsurface. And usually that boundary between highly oxidizing and highly reducing is the level of the water table. So at or above the water table, the system is very oxidizing. Below the water table, conditions are very reducing. And what's important about this is that iron is very soluble at reducing conditions, but very insoluble at oxidizing conditions. And copper is exactly the opposite. Copper is very soluble in fluids in oxidizing conditions and very insoluble at reducing conditions. So what does that mean? That means that iron wants to go into solution in the subsurface, but as it's transported to the surface, it wants to precipitate out. And so it forms a set of iron-rich oxides and oxyhydroxides. These typically whether red or red-orange or red-orange-brown and form a deposit that's called a gossan. The gossan is not economic itself, but it can indicate economic deposits at greater depth. Copper is weathered out of the pluton at the surface because it's more soluble under oxidizing conditions, and it percolates downward and precipitates where conditions are more reducing. This produces a zone that's highly enriched in copper, and it's called a supergene zone. Supergenes are simply areas that are highly enriched in economic minerals. In this case, it's a copper supergene. So here's the question for you based on that. What drives differential mobility of copper? It says something to do with oxidation, but is it that iron is more soluble or is copper more soluble under oxidizing conditions? And here I've shown what the relative enrichment of these elements would be for the surface versus the subsurface. Maybe that will help. And the answer here is that oxidized iron is less soluble, so it migrates upward and is deposited under oxidizing conditions. Oxidized copper is more soluble, so it migrates downward and is precipitated under more reducing conditions. And this gives rise to a layering of metals where iron is concentrated towards the surface, copper is concentrated towards the subsurface. With this brief introduction and a little bit of review, I think students would be able to say something about the distributions of iron versus copper minerals associated with porphyry copper deposits. The last thing I want to touch on is reflected light microscopy. Oftentimes in these classes, we talk about transmitted light microscopy, looking at thin sections. But for many economic minerals, which are either oxides, oxyhydroxides, or sulfides, we can't see through them with transmitted light. However, they can differ considerably in the way that they reflect light. Here, for example, is a reflected light image of an ore. It has several different minerals in here. This light yellow mineral that's highly reflective is pyrite. Pyrite's a little bit harder, so it tends to accumulate scratches. It's harder to get rid of those scratches than the other minerals. This is arsenopyrite, so it's an arsenic-bearing iron sulfide. Pyrrhotite is over here, this kind of pinkish mineral. Pyrrhotite is another iron sulfide. It has a lower content of sulfur relative to iron. This is chalcopyrite, distinctively yellowy orange in reflected light. And this extremely reflective mineral over here is gold. So if we looked at this rock in transmitted light, all we would see is black. We can't pass light through any of these minerals. However, in reflected light, we can pick out 1, 2, 3, 4, 5 different minerals that we would otherwise not be able to recognize. Now, there are lots of optical properties that we look for in reflected light, just as in transmitted light. We can look for cleavage. Some of these minerals have cleavage. Color is important. Like I showed before, there's several different colors for different minerals. There's the reflectance of the mineral. That's the intensity of the reflected light, completely independent of what its color is. So for example, if we look back here, gold is extremely reflective, much more so than pyrite or pyrrhotite or even arsenopyrite. Bireflectance is the change in reflectance when the stage is rotated. So these are all examined in a petrographic microscope with a rotating stage. And the reflection can be pleochroic, so there can be a change in color when the stage is rotated. Now, there are lots of things that you can see in reflected light. In addition to seeing different minerals, you can see exsolution of one mineral from another. You can see one mineral replacing another. Or you can see textures that tell you the sequence of mineral precipitation. And there's some great resources. There's a book on ore microscopy and ore petrography published, well, now it's 30 years ago, but you can find this open access on the Mineralogical Society of America website. And Dan Gregory has posted several different YouTube videos that show these different minerals in reflected light. So here's some examples of what I was talking about. This is cleavage in galena. Galena has very good cleavage, and it produces these characteristic triangular pits in polished grains. Here is the mineral digenite intergrown with bornite, and there is late-stage covellite that is replacing the digenite along mineral boundaries over here and fractures that run through here. Here is an example that illustrates the intensity of the reflected light. Pyrite, galena, and chalcopyrite are all very reflective. Silicates, which are this gray region down here, are not very reflective. And the difference is, it's not just the differences in color among these three minerals, it's also the differences in reflectivity that allow you to identify them. Here's another example. These are little blebs of galena, highly reflective, much more reflective than the bornite that's here or the magnetite. This is a great image of molybdenite. Molybdenite commonly has these deformation features to them. So these are little kink folds because it's a highly layered structure. And the kink folds allow you to see that when the mineral is in this orientation, it's darker, and in this orientation, it's lighter. So if we rotate the stage, we would find that the light areas gradually become darker and the darker areas gradually become lighter. That's an example of bireflectance. Here's an example of exsolution. There are tiny laths of bright yellow chalcopyrite that have exsolved from bornite, and I'm not sure what this is. This might be digenite. There's also some late-stage covellite in this image. And here's another example where chalcopyrite and cubanite have been intergrown. Chalcopyrite and cubanite, which is another copper iron sulfide, form a solvus, and as they cool, they can exsolve chalcopyrite laths within cubanite and cubanite laths within chalcopyrite. Here's an example where we can see a series of reactions. There's yellow chalcopyrite that forms most of this field of view. It has a rind of bornite on top of that, and the bornite has a rind of covellite. So this indicates something about the paragenesis. First mineral to form was chalcopyrite, then bornite, then covellite. So that finishes my discussion of reflected light microscopy. I do recommend looking at these online resources. They really are quite good for illustrating just how reflected light microscopy works and how it can be used for interpreting ore paragenesis. Thanks.